Good afternoon, or good morning, or good evening to everyone. We're going to report on the lab activity 13 entitled Reactions of Carboxylic Acids. And we are the group 5. So, if you have listened to what we have discussed in our ChemLec, this is just a review or a study of what Ma'am Eroy explained. So one of the important properties of carboxylic acid is the reaction of the ionizable hydrogen. Carboxylic acids react with water as follows. RCOOH plus H2O. We're going to have H3O plus RCOO negative. So it became H3O because the hydrogen from the RCOOH, which is our carboxylic acid, nag-transfer sa aton nga H2O. So the equation indicates that the reaction does not proceed appreciably to the right and that most carboxylics are therefore weak acids. If the acid has been substituted by an electron attracting group or element on the A carbon like chloroacetic acid CH2Cl COOH, its strength as an acid is markedly increased. Carboxylic acids react with bases to form alkali salts, which generally are soluble in water. This reaction is possible because of the acidity of the carboxyl group. The equation is as follows. So, a number of reactions of carboxylic acids involves the replacement of the hydroxyl group in the COOH. One of these is the reaction with alcohols. The replacement of the OH by the OR group of the alcohol leads to the formation of esters. This reaction is often acid catalyzed. Carboxylic acid is the one with the RC double bonded O and OH plus H, then OR, then we will have the R, C double bond with O, OR plus H2O. So the formation of esters is usually detected by the evolution of pleasant odor.
So, in the carboxylic acids are relatively resistant to oxidation. However, some acids like hydroxy acids and other multifunctional acids may be oxidized. So the CH3 CH double bonded to OH COOH oxidized to potassium permanganate is equivalent to CH3 CHO plus CO2 plus HOH. And then COOH bonded to COOH oxidized to potassium permanganate is equivalent to 2CO2 plus HOH. With a tolerance reagent, a mild oxidizing agent, the COOH bonded to COOH plus Ag, close and open parenthesis NH3, 2 plus, is equivalent to 2CO2 plus Ag plus 2NH4 plus. And then HCOOH plus Ag, close and open parenthesis NH3, 2 plus is equivalent to 2CO2 plus Ag plus 2NH4 plus. For the objectives, so first is to determine the pH solutions and to test its solubility. Second is to determine the effects of oxidizing agents. And third, discuss the concepts involved in the reactions of carboxylic acids. For the procedure, in acidity and structure, determine the pH of 0.1 m solutions of acetic acid, monochloroacetic acid, and trichloroacetic acid. For the solubility in water and in 10% of sodium hydrogen carbonate, is first is using a 0.5 ml of the liquid sample or 0.5 grams of the solid sample. Test the solubility of acetic acid, benzoic acid, oxalic acid, succinic acid, and adipic acid in water. Second, add water in 0.5 ml portions until a total of 3 ml have been added. Note the volume of water needed to dissolve the acid. Record results. Third, test the solubility of the same acids by using 10% of sodium hydrogen carbonate solution instead of water as a solvent. Note any evidence of reaction. For the ester formation, first to 10 drops of ethanol in a test, add 4 drops of dilute acetic acid and 1 drop of corn sulfuric acid. Second, warm, note the odor of the ester. And third, repeat the esterification process using methanol, salicylic acid or 0.1 grams, and sulfuric acid. Note the odor of the ester after pouring into a beaker containing 1 ml water. For the effects of oxidizing agents on the carboxyl group, the alkaline potassium permanganate first is to, in each of the 9 test tubes, add 5 drops respectively of formic acid, propionic acid, lactic acid, tartaric acid, citric acid, benzoic acid, oxalic acid, and succinic acid. Place 5 drops of water into another test tube which will serve as a control. Second, render each alkaline with dilute sodium hydroxide. Add 2 ml of 0.1 potassium permanganate solution to each test tube. Note any change in color. Third, heat gently to boiling. Observe any color change. Fourth is to record your observations and possible inferences based on the differences in structures. And for the tallest reagent, first is to prepare tallest reagent to 2 ml of 1% of silver nitrate, add 1 drop of sodium hydroxide, and add drop by drop dilute ammonium hydroxide with shaking until the precipitate which forms just dissolves. Second, divide the tallest reagent into 2 test tubes. To one, add 5 drops of formic acid. To the other, add oxalic acid solution. Third is warm gently over a water bath. Note your observations and give the possible inferences.
Okay, so for our data and results, since we do not have enough time to conduct this laboratory experiment, the data and results that we will be discussing Okay, sorry for that. So in continuation, since we do not have enough time to conduct this laboratory experiment, the data and results that we will be discussing are solely based on sources from the internet. Hence, some tables and questions are left unblank because we were not able to find sources to answer those, and some of them needs to be answered through actual conduction of the said experiment. So for the acidity and structure of carboxylic acid, the structural formula of acetic acid, monochloroacetic acid, and trichloroacetic acid are presented on the table. For the pH level of acetic acid, it is roughly equivalent to household vinegar, which has a pH level of 2.4. For the monochloroacetic acid, there were no sources can be found. And for the trichloroacetic acid, which is considered to be the strongest acid that has a pH level of 1.2. Next slide, please. And for the follow-up question, what is the effect of chlorine on the acidity of carboxylic acid? The presence of chlorine atoms clearly increases the acidity of the carboxylic acid group. Since the chlorine atom is electronegative in nature, so it stabilizes the stability of conjugate ion by taking off the negative charge towards itself. Hence, due to the better stability of conjugate base chlorine, increases the acidity of acetic acid. So the number of chlorine atoms is directly proportional to the acidity of the carboxylic acid. And to simply put, when the number of chlorine increases, the acidic it is. Next slide, please. Okay, so now let's move on to the solubility of different acid samples in water and 10% sodium hydroxide. The structural formula of acetic acid and benzoic acid is already presented in this slide. And acetic acid is infinitely miscible in water. And when we say miscible, it means it forms a homogeneous solution. Hence, it is soluble in water. And benzoic acid is not very soluble, but as the temperature of the water increases, it becomes more soluble in water. By that, benzoic acid is temperature dependent for it to be soluble in water. And both acetic acid and benzoic acid are soluble in 10% sodium hydroxide. Next slide, please. And for the structural formula of oxalic and succinic acid, still it is presented in the slide. And for its solubility in water, oxalic acid is soluble, whereas succinic acid is only slightly water soluble. And for their solubility in sodium hydroxide, there were no sources can be found, so we leave it blank. Next slide po. And lastly, for the adipic acid, its structural formula is presented on the screen, and it is insoluble in water. And still, no sources can be found regarding its solubility in sodium hydroxide. And for the follow-up question, explain the effect of structure on solubility. Explain also the differences in solubility in water and in sodium bicarbonate solution. So there were no sources can be found, but when it comes to how structures affect solubility, two substances will often dissolve in one another if their molecules have very similar structures and as a result, comparable intermolecular interactions. And two substances with distinctly different molecules won't randomly mix.
Am I audible?
Yes,
React daw ng heart if... sige, so... Next is for the ester formation. We have two procedures, and the first procedure is ETOH, or also known as ethanol, plus acetic acid, plus sulfuric acid, and the observation of this procedure and noted the other, and the result is that it has an ethereal, sweet or fruity odor with a sweet grape or cherry taste. Next is the chemical equation. The chemical equation of this procedure is ethanol plus acetic acid plus sulfuric acid yields to ethyl acetate. And the next procedure is METOH, or also known as methanol plus salicylic acid plus sulfuric acid, and the observation of this procedure and noted the order of this procedure and resulted to sweet fruity aroma resembling a mint, and it tastes like peppermint and wintergreen. Next is the chemical equation. The chemical equation of this procedure is methanol plus salicylic acid plus sulfuric acid yields to methyl 2-hydroxybenzoate. So, next slide please. So, give the names and structure of the esters for the above reactions. So for the two procedures, which are ethyl acid, which are yields to ethyl acetate and the methyl to hydroxybenzoate, the structures are presented on the screen. So next slide, please. So next is the effects of oxidizing agents, the alkaline KMNO4. So since it is not conducted in the laboratory, I will just show the structural formula of the following carboxylic acids. So the formic acid, and this is the structural formula. And for the acetic acid, this is the structure formula. And for the propionic acid, this is the structural formula. And the lactic acid, this is the structural formula. Next slide, please. So next is the tartaric acid, and this is the structural formula. And next is the citric acid, and this is the structural formula. Next is the benzoic acid, and this is the structural formula. And next is the oxalic acid, and this is the structural formula. Next slide, please. So next is the succinic acid, and this is the structural formula. And lastly, next. So for the tolerance reagent, the two procedures were not also laboratory conducted. So the two procedures, which are the tolerance reagent plus formic acid and tolerance reagent plus oxalic acid, have an observation of no tests conducted, and we also cannot find a source to the observation of these procedures.
So for the conclusion, even though we didn't conduct this laboratory activity, we still learned a few things from it. We discovered that the presence of chlorine atoms significantly raises the acidity of the carboxylic acid group, which is why we learned about how chlorine affects the acidity of carboxylic acids. Due to its electronegative character, the chlorine atom stabilizes the stability of the conjugate ion by drawing the negative charge away from itself. Thus, chlorine makes acetic acid more acidic as a result of the conjugate base's improved stability. Additionally, we now know the chemical formula and pH of each carboxylic acid. In terms of the effect of structure on solubility, typically two substances will dissolve in each other if their molecules have highly similar structures and, as a result, similar intermolecular interactions. On a microscopic level, two substances with very distinct molecules won't mix at random. In general, nonpolar materials dissolve other nonpolar materials, whereas polar substances dissolve other polar compounds. The lower the mutual solubility, the higher the difference in molecular structural and intermolecular attractions. That's all for our report. Thank you for listening and watching this video. If you have any questions, feel free to message Mom Ethel. Thank you.